This is TAU Unbound, the English language podcast of Tel Aviv University. Please welcome your host, Ido Aharoni, Tel Aviv University's graduate, member of the Board of Governors, lecturer, writer, and veteran diplomat.
Welcome to TAU Unbound, the English language podcast of Tel Aviv University. I'm your host, Ido Aharoni, and today it is my pleasure to welcome Professor Yaron Oz from the Department of Physics and Astronomy. Welcome to the show.
Thank you. Good to be with you.
I read your bio. It's so impressive. You published over 150 scientific papers, which is incredible because, most people can't even grasp the magnitude of your academic work. But before we begin discussing your academic work, tell us a little bit about yourself. I see you were born in Haifa, 1964.
Yeah, these are the right numbers, yes. So, I grew up in Haifa. I'm the youngest. We are five kids in the family. I'm the youngest. And as you probably guessed, my mother wanted me to be a medical doctor. And so that was okay until when, I got to the 6th grade, and then I understood I will be a physicist, and that's it.
Now, when you were a kid, it was around the same time I was a kid. I was born in 1962, so I'm 2 years older. But the name Yaron Oz was very famous in Israel because it was a very famous football player.
Of course.
And
yes.
so I guess you had to live up to that expectation, right?
Well, actually, it's an interesting thing. When I moved back from CERN to Tel Aviv, I lived in I lived in Ramat Aviv Gimel, which is the same neighborhood where he lives, and actually they called him to ask where is Professor Yaron Oz, and then I understood that I made it.
That's a good one. People called him. I think he's in insurance or something, right? He's an insurance agent or something.
I have no idea, but he was actually, a great football player, as you said, at that time. We were kids, we were playing, in the neighborhood, and we were worshipping these guys in Maccabi Tel Aviv.
Now, you grew up in Haifa. Obviously, Haifa is known for its strong academic foundation. Your mother wanted you to become a medical doctor, yet you were drawn to physics and astronomy. What happened?
Well, I think I was always good in math and physics. It was just that the expectations were that, medical doctor is something that is needed in the family. And since the other four kids decided that they will not go into medical studies, so I was the last one, the last hope. And so, and at the end, I also didn't do it. But, to be a medical doctor, it should be, something that you want to live with. It's different.
Right. It's a different kind of commitment. Was there a specific event or a series of events that convinced you that this is your career path?
Well, I'm not sure there is only one, but I can tell you a couple of interesting stories. When I was a kid, like maybe, I don't know, 3rd grade, maybe 4th grade, there was in one of the newspapers, I think it was Ido Aharoni, one of them, like a question in math. And I solved it and I sent them that. And I got as a prize, these small computers. At that time, they were really very tiny calculators. But it was the first one that I got. And I think it was about 3rd or 4th grade.
So that was a positive reward. So you said, here I'm being rewarded for my excellence. I may continue in that direction.
Yeah, not sure I thought in this way. But it was clear that was sort of the path.
So your initial attraction was to physics or to astronomy?
I was always doing math and physics at the same time, and the choice of particular discipline was only much later. But, for physicists was always to go in the footsteps of Albert Einstein. That's what we all wanted to do, And we went into that direction, more formal and theoretical physics.
And of course, Albert Einstein is teaching us some very profound lessons because everything that he achieved through thought experiments. Is it something that scientists today appreciate, the fact that he did all that he did without budgets, without laboratories, without staff, just using his imagination?
First of all, yes. And he was actually great at this, he had these great skills, and every theoretical physicist is trying to develop the same skills. Except that he also knew the experimental data at the time. It's not that he was completely disconnected from the experimental data. He knew exactly what was happening in that field. But his talent was to understand among all this experimental data what is actually more important and what is less important. And typically there is like one or two things which are important and all the rest you can just forget about it. And he knew exactly, where to aim. That was his talent.
Now, you were educated at Technion, like a good boy from Haifa, but then you moved to the United States where you spent time at UC Berkeley, which is a suburb of San Francisco. This was in the late 1980s. Is there anything, I'm sorry, late 1990s? Is there anything that you can share with us about that period at Berkeley?
Yeah, actually, I had the PhD while I was in the military service, and when I finished the military service, I needed to go for a postdoc, and then I had to choose East Coast or West Coast, like Harvard, Princeton, or Berkeley, Stanford, that area, and I decided that the weather is the most important factor, so I went to Berkeley. It was actually a good time.
Because here in Israel, if you'll ask the average Israeli, they'll tell you that UC Berkeley is a bastion of anti-Israel sentiment. I must say, as someone who lectured there many times, I didn't encounter any problem at UC Berkeley. Was that your experience as well?
Yeah, actually, there is a clear difference between the exact sciences and all the rest, like, humanities, anthropology, social sciences. The things that you hear about are mostly in those disciplines.
Yeah,
in the exact sciences, you don't see that. You don't feel that.
In the humanities and more social
there
studies.
There you feel it much more, yeah. So I didn't have any experience like that.
Now, in 2002, you served in CERN in Switzerland. Israel joined CERN officially, I think, in 2010.
Right.
Can you tell us a little bit for the benefit of those of our listeners who never heard of CERN? What is CERN? What is the importance of it? Why it's so important to have an Israeli scientist like yourself there?
Right. Actually, for me, it was even an interesting experience because I never thought about applying to a job in CERN. Actually, they contacted me, and it was very strange because at the time we were not members of CERN, and I didn't know that even Israelis can have a faculty job at CERN. The place is actually very important for high energy physics because for many years it dominates the large accelerators, and which are the experiments that high energy physicists do. Basically, they scatter particles and they are trying to understand what is the physics at very high energies.
So let's stop here for a second. Again, let's assume that the people that listen to us don't really understand science at the same level. So what is it that they're trying to achieve when they observe the behavior of particles?
Right, so the idea is very simple actually. Like if you take two stones, you break them, you will get, you hit one against each other, you will break them, and then you'll get smaller stones. And then you can continue. The question is, if you do it more and more and more, with higher and higher energy, higher and higher power, right? What are you going to find? Are you going to find the same physics that physics of stones, or you're going to find something totally different? What we do know is that you're going to find something totally different. There are certain energies at which the physics will be different than our intuition.
Can we learn from that? This is inward, right? Breaking, going down. Can we learn from it outward? If we had an imaginary space shuttle that would fly forever with unlimited amount of energy, where would we get?
So you can learn. You're talking about the large scales compared to the small scales, and there is a relationship between the physics at the small and the large scales. For instance, when you are trying to understand the origin of the universe, you have to understand what we call quantum physics, the things that you are studying at CERN and in other experiments like that.
Which is also your area of expertise, quantum physics, and we will get to that later. So let's go back to CERN. So CERN is looking at the smallest possible particle, what kind of energy drives them, and why is it so important for Israel to be part of that project?
So I think, when we play soccer, we want to play with the best, right? Let's say Europe. Basketball, we want to play, with the best that we can. Sports in general. Same in science. You do not do science only within your borders. You have to be, the league where the big players are. And so it's important to be there for this reason. I think there are other benefits. Other benefits are, let's call them political, in the sense that it's not just that we are scientifically involved with these other countries. it has other spin-offs, other effects, good relationships, etc. So I think there are other reasons for that. But scientifically, you really want to be where the big players are.
Let's talk about your department a little bit, about your students, about the scientists that you work with. How would you describe what makes them unique in your view?
I think these are typically people that are curious. They would like to solve interesting problems, and they don't care too much about the material benefits. So in this sense, they are very special people. They were like that probably as kids, and then they grew up and remained as adults like that.
And this definitely serves as a social glue, right? As a bridge that brings communities together. Can you share with us some interesting human stories that are happening in your department?
Yeah, so there are relationships that are being built, the language that is being built. When people talk with each other, there's a certain language that if you'll just, you will be an outsider, it will be very hard to follow. And I can tell you also all kinds of interesting stories about Israel viewed by other scientists. So I'll give you an example. Actually, when I arrived in Berkeley, so one of my colleagues was a Japanese colleague. He was a very good excellent scientist. And at some point we discussed what's the population in Israel. And he said, well, I estimate about 80 to 100 million. So I asked him, how did you estimate 80 to 100 million? I mean, it's like an order 10 mistake. He said, I see how many Israelis are in quantum physics, how many Japanese are in quantum physics. It's comparable in the number. So that's how he deduced what's the population.
Do you have any international colleagues here at Tel Aviv U?
You mean international that are faculty at Tel Aviv
Or just students or people that come to participate in research?
Oh, we have many all the time. Typically we have postdoctoral fellows on regular basis. We have visitors, people on sabbatical. We have our colleagues abroad. We have joint collaborations, joint research grants. We have all kinds of agreements also with different institutions. So yeah, we are pretty much well.
And in terms of our collaboration at Tel Aviv U with other institutions, where would you say is the strong part? Where would you like to see more invested?
You mean in terms of the places or in terms of the money? Or
Geographically.
Geographically. So geographically, we are actually strong in the US, but also in Europe. It used to be that the relationship with US were much stronger, but now they are very strong in Europe as well. And they are developing also with the East, especially India, China, Japan, and other places. So I think we're pretty much connected internationally.
I think that's amazing because, Tel Aviv University is in Tel Aviv. Tel Aviv is really the beacon sub-brand of the State of Israel, really has a great reputation all over the world. I think that the relationship between Tel Aviv U and the city of Tel Aviv is very similar to the relationship between New York University and the city of New York. And that's wonderful to hear. Now let's jump into your area of specialty. So quantum became a buzzword, right? Everybody talks about quantum computing, quantum physics. What is it? What is quantum?
It's actually an excellent question. So we distinguish as physicists between classical and quantum. So what is classical? Classical is what we do, what we see in everyday's life. It's the way we evaluate, the speed of the car and when it will arrive at a certain place, with a certain speed, etc. It's the physics of rockets, airplanes, ships. It's even the physics of the animals who are chasing each other. So that's the intuition that we have. It's the physics of these big objects. And the rules for that, the laws, were actually found many hundreds of years ago by Newton. And that's actually what you learn also in high school. But then if you go to the smaller particles, and by smaller I mean really, really, really much smaller, 10 orders of magnitude smaller, like the atoms, you would think that maybe the physics is the same. But how would you know? I mean, you cannot really watch these atoms, how do they move, etc. It's very difficult. They are too tiny. So you do all kinds of experiments. And what you find out, that the rules are very, very different than the rules that we know. And they are very non-intuitive. So I can give a couple of examples of why they are non-intuitive. For instance, one example is like that. Suppose I need to come from my office to here, to this place, to talk with you, right? I take one path, and I come. Now, suppose I am an electron, or a photon, or a small particle. How that particle will come from my office to this place? He's going to go on all the possible paths, the directions at the same time. All of them. You go in all of them at the same time. Now you'll ask, okay, but now I'm going to insist to ask this electron, what is the path that he took? Then in one measurement, you will find him in one place, in another place. And that will be the experiment that will tell you that he actually went in all directions.
And there's also an impact about the relationship of that particle with other particles, right? So one thing that happens here can affect something that happens in entirely different place.
Right. That is another weird thing. Einstein used to call it spooky action at a distance. He actually discovered it, as you said before, by a Gedanken experiment. It was not real experiment. It was just using the brain. And what he discovered is that these rules of quantum mechanics, they create something very, very funny which we don't understand. And by the way, we do not understand it until today, even though it has been established experimentally. So in order to explain it, I'll give you the example. But first I need to tell you what does it mean action at a distance. Okay? So it's all of us know that we are moving around the sun. Okay, and the reason for that, there is a gravitational force. Now I ask you a question. Suppose somebody took the sun and removed it. Now there is nothing to move around, right? You would say, okay, then we will take another path. Not true. It takes about 8 minutes for this information to arrive from the sun to us, and only then we will know that there is no sun. And until then, we will continue to rotate, because we think there is a sun there. So there is no action at a distance. Things don't happen immediately. But this thing that he discovered is something like that. This is called entanglement. And the way it works is the following. Let me give you another example of something which we call classical correlation, and then I'll distinguish it from this entanglement. So classical correlation means the following. Suppose both of us do an experiment where 2 balls. One ball is red, one is blue. We look at them, we close our eyes, each one takes one ball, and we just leave. And then we go like 100 kilometers one from each other. You look at the ball that you took and you see red. What do you know immediately? That mine is blue. This is called classical correlation. You deduce an information even though very far. Not a big deal. But now suppose I told you that before you looked at the ball, actually there was no color there. Only when you looked at it, you chose a particular color. And then you immediately, you forced my color to be the other one. That's entanglement. So actually there is an action at a distance in some sense, or a correlation at a distance, and this is a very powerful resource of quantum physics. Yeah.
Now, this is theoretical. What are the practical applications of this knowledge, of the theory of entanglement?
Oh, there are many, many things that you can use it. But before we do quantum computing, let me just tell you about something else, teleportation. Probably you have seen these Star Trek movies, right? When they were beaming Scotty from place to place. Now you could ask whether this is possible. Okay? Actually, it's possible. Not for humans, but for small particles. You can use entanglement between 2 places in order to transmit a particle from one place to the other. And this transmission is indeed the teleportation. So you can use this information between the 2 places in order to share things that otherwise classically are impossible to do.
Now, I remember when I was much younger, there was a television show called Quantum Leap about a person who was able to leap in time. And I guess the reason why they used the word quantum is exactly what you just described. I don't know if you remember that. Scott Bakula was the lead actor. Mm-hmm. And that was a very, very popular show. So what are the applications when it comes to the world of computers?
So first of all, I need to explain what is a quantum computer, which is different than classical computer. Classical computer works with bits, zeros and ones, off and on. And then you work in this basis and you can do any calculation that you want, multiplication, addition, anything you can do with this classical computer. Quantum computer works differently. First of all, the bit is replaced by something is called quantum bit. It's a qubit. Now the qubit has this thing that it doesn't have to be 0 or 1. It can be any value. It's called the superposition. It's like when I told you that the particle who comes from my office to your office is not going to take one path, it takes all of them. This one can be both 0 and 1 at the same time. Now it's kind of weird, but that's the situation. And then the way the quantum computer works, it works on these qubits. But because it has this thing that you can be at the same time at 0 at 1, you can do calculations that you could not do with ordinary classical computers. Entanglement, that we can actually connect different parts of this software, for instance. And so that I do something in some place in the computer, it affects the other ones in the other side. And that actually speeds up a lot the calculation.
So what are the applications of it? So let's say we have a computer that can calculate things with much greater power than the traditional computer. What are the applications of it?
So it's volume of data and speed. And once you have that, you change dramatically the whole shape of the industry and the security. So let me give you an example in security, and then we can discuss industry or any, banking, finance, drug discoveries, etc. Suppose I give you two numbers, 3 and 5, and I ask you to multiply. You will tell me it's 15. Suppose I ask you what are the prime factors of 15, you will tell me 3 and 5. It's not a big deal. But it turns out that if I give you very large numbers, prime numbers, and I multiply them, it's easy to multiply, but to go in the opposite direction and discover them, it's a very difficult problem. This is the basis for all the security protocols that you know in the world, finance, military, etc. Turns out, quantum computer can break it. So by now already there are many who collect a lot of data, and they hope that once quantum computer will arrive, they will be able to use it in order to, understand decipher what's in them. That's a security issue. But on the other things, for instance, discovery of molecules that can help you in drugs. These are complicated problems. Or batteries, lithium batteries, just to understand the components, reactions, etc. Finance, banking, if you want to do, portfolio analysis, etc. So it has actually an applications on everything because we are dependent on computers. And once computers become much stronger, but by much I mean much stronger, and can, analyze much larger volume, it's a huge impact on our life.
Now, how far are we from that point in time?
Right. So that depends what we are talking about. There are several types of computers. There are the ones that are simple, that can do very little tasks, like the ones that Google has. Those are not very interesting. They are interesting academically, but they are not. They cannot solve a problem that which is interesting for us. The goal of most of the companies is about 2030. Well, like 2030, they will have a significant computer. It's not something we can buy. It will be in the cloud, but you will be able to use it, and then it should be something that classical computers cannot do. That's the goal. Whether it will be reached is not clear.
Now, is that goal requires, I would assume, a great degree of international collaboration, countries working together, universities, scientists. Can you map this coalition of scientists that are working towards 2030?
Right. So I would distinguish between universities, government funding, and companies. So governments all over the world, for various reasons, decided to invest a lot of money in this. Basically, Europe, US, China, all the others. Also, Israel, by the way, has a national program for quantum, which is more modest than all these other countries. And of course, all the academics in the world. But then there are the companies that want to make money. And those ones have invested billions of dollars of their own in order to build it.
These are the tech giants.
These are the tech, like for instance, Google, Amazon, Microsoft. Each of them has its own technology. But this is actually for the purpose of basically making money.
Right. So these will be commercial applications. What do you think Israel should do in order to become a leader in the field of quantum computing?
Right. So I think Israel already understood that in some sense we are still lagging behind. I mean, we were good in cybersecurity, AI, classical computing, etc. And the reasons were that it was important basically for the military and others, and they understood it's important. It was not clear in the past that quantum is important. Now it became clear. But typically in Israel, the way it works is that then once we understand that, we start to move to run very, very fast. And what needs to be done is definitely government's funding, that's for sure. We need to also raise scientists, teaching programs, etc., etc. We need to be part of the international ecosystem, so we have to work with all the others. And we need to do what we normally like to do, build startups.
And are you optimistic about the role that Israel and Tel Aviv U can play in the future of quantum computing?
Yeah, I think yes. I mean, the main advantage of Israelis is they are, talented and very fast. So these are qualities that are needed. And I think we will just, close the gap within 5 years. We are not going to build the biggest quantum computer. We never did. But I don't think it's important. I mean, Google can do it. Somebody else can do it. But we can be major players in the field. And once this will be developed, there will be quantum machine learning and quantum cybersecurity and all kinds of things, which we are very good at.
Well, this is a wonderful message for our listeners to end our podcast with, which is it's all about the idea. Victor Hugo famously said that there's nothing more powerful, there's nothing stronger than an idea that its time has come. And what we learned from you today is that the time for quantum computing has come. And it's a very powerful concept that can change our lives. And I'd like to thank you for educating us and educating myself about such an important area. And really keep up the good work. You're doing an amazing work. And to our listeners, I'd like to thank you for being with us. And until our next episode, bye-bye from TAU Unbound.
This is TAU Unbound, the English language podcast of Tel Aviv University. Please welcome your host, Ido Aharoni, Tel Aviv University's graduate, member of the Board of Governors, lecturer, writer, and veteran diplomat.